And looks at C double bond C containing compounds that are alkenes, and C triple bond C containing compounds that are alkynes, their properties, and the reactions that they undergo. Let's see what we need to know from this chapter. Like I said, alkenes are the C double bond C. Alkynes are C triple bond C. One example of an alkene is ethylene. These compounds tend to be the carbon-carbon double bond makes these trigonal planar, because as you can see around each carbon, now there are only 3 groups around each carbon. So the angle is 120, the shape is trigonal planar. Alkynes, on the other hand, tend to be linear, because as you can see, each carbon now has only 2 groups around it. The simple formula for alkenes are CnH2n. Alkynes are CnH2n minus 2. So for alkanes, the formula was, to remind you, CnH2n plus 2. And interestingly, alkenes and cycloalkenes share the same general formula, CnH2n. From an exam point of view, please do memorize these formulae so that then you can recreate whatever 2-carbon, 3-carbon, 4-carbon compound that you might encounter. But also, if I gave you a formula such as C2H4, you can very easily tell that that is an alkene or a cycloalkene, although there is no 2-carbon cycloalkane, it only starts from 3 carbons, based on the number of N to N. These also tend to be nonpolar, just like alkanes, and so just like alkanes, their physical properties are going to be the same. They're going to be insoluble in water. They're going to be mostly liquid and gases. They are, as a whole, called unsaturated hydrocarbons. This is very important to learn. Alkanes are saturated hydrocarbons, whereas alkenes and alkynes are unsaturated hydrocarbons. This is similar to saturated fatty acids and unsaturated fatty acids, and there's this whole debate on which one might be better for you. And so this is the basis. Alkanes only single bonds, and so we call them saturated. When they have double and triple bonds, we call them unsaturated. When we write condensed structures, and we practice this a little bit, when we write condensed structures, do not eliminate the double and triple bond. Just keep them as is. You can omit the single bond lines, but you may not omit the double bond and triple bond lines. We will skip the IUPAC naming of alkenes and alkynes, but they are similarly named than alkanes. The same sort of rules apply. You're looking at the longest chain, 1, 2, 3, 4, for example, here. So it will be a bute, but instead of an ene, if it is an alkene, it will be E-N-E-E. And if it is an alkyne, it will be Y-N-E, 1, 2, 3, 4, 5, 6. So this will be an hexyne. And then, of course, the substituents come in. So it will be methyl butene. But now you realize that you have to name it this way because you want to give the lowest number to the substituent. So it will be 2-methyl butene. And by the same sort of card, this will be 3-ethyl hexane. Again, I don't think I will give you alkenes and alkynes for the exam, but it's always good to know what these are named They're pretty much the same as alkanes, except that now you have to use Y-N-E or E-N-E depending on whether it's an alkene or an alkyne. You have two sets of double bonds. It's called dienes, and that's just another terminology. So any compound having two double bonds are going to be double bonds, dienes. Similar to alkanes, cyclopropane, cyclobutane, etc. Now you can have cycloalkenes too. And so I'm just going to show you a few examples here, but again, we don't need to focus on the name. The big difference between alkenes and alkynes are the fact that with alkenes, you had rotation around the double bond. So you could have a Cl here, for example, a Cl here, another Cl here, and these would flip or rotate, and it's fun. Whereas with the butene, you do, along this double bond, have very restricted rotation. Therefore, you have what are known as isomers. So if the substituents are on the same side, we call them cis. If the substituents are on opposite sides, we call them trans. Please watch a separate video for cis and trans isomers. But this is a special type of isomerism in alkenes and alkynes that comes out of the fact that the rotation around the double and triple bond is restricted. Restricted rotation. You have 4 different groups here. And you can have the 2 groups on the same side. If you have the 2 groups on the same side, then it's a cis isomer. If you have the 2 groups on opposite sides, you have a trans isomer. So here, actually I misspoke. We're not a separate video on cis and trans isomers. I think this will be sufficient. These two, formula-wise, they are the same. So you have 1, 2, 3, 4 carbon atoms, so we call it a butene. However, here the methyl group, the ethyl group is here. Here, the ethyl group is here. These are identical on this side, and these are identical on this side. So now these two are the same. However, supposing if you had a butene that was 1, notice that this is a butene too, because it's 1, 2, 3, 4 carbon atoms, so it's still a butene. And this one is 2. But in this case, the methyl groups are on the same side, and so we call that cis. On this case, you have the methyl groups on opposite sides, so we call it trans. This is similar to trans fats. The idea of trans fats comes into play when you have the groups on the opposite side. Now, these stereoisomers, as I called cis and trans, or stereoisomers, they don't differ in how the atoms are linked. They differ in their 3-dimensional arrangement. I will show this to you in class using ball and stick models when we meet. Now, fatty acids or carboxylic acids, we've gone over this functional group. Okay, but they do have double bonds as well. And therefore, they're able to undergo the cis-trans isomerization, or otherwise known as stereoisomers. Now, saturated fatty acids, they have no double bonds. Unsaturated fatty acids do have double bonds. So you do have saturated fatty acids, but you also have unsaturated fatty acids. When you do have unsaturated fatty acids, those that have double bonds, those fatty acids naturally occurring are cis. For example, coconut oil has cis fatty acids. But then there are, fatty acids are generally solids. Oils have a large number of double bonds and they tend to be liquids. This is a large molecule, lycopene, which is found in watermelons. It's having several double bonds, so it's an example of an alkene. Lycopene, E and E is going to tell you it's an alkene. It's an antioxidant that prevents unwanted oxidation from occurring. Tamoxifen, again, you can see that C double bond C. It is a drug used in treatment of breast cancer. You also see, again, some more double bonds here. These are oral contraceptives or birth control pills. They're designed to mimic natural hormones in the female, such as estradiol and progesterone. They contain a double as well as triple bonds. Alkenes generally undergo addition reactions, not substitution reactions. Undergo what are known as hydrogenation reactions, where you can react it with a hydrogen to break that double bond and to replace it with hydrogen. This is the reaction that I would like you to learn, hydrogenation. So with hydrogenation, you have an alkene. It adds itself to the hydrogen. It is generally accelerated by using a metal catalyst such as nickel. And what you can see is across the double bond, instead of the double bond, now you have a single bond. And where there were other things, now there is hydrogen. Because remember, if I take away one of the bonds, now I have made two spaces for extra hydrogen to come in. Nickel is one catalyst, palladium is another one. Pd is usually shown on the arrow because it is a catalyst. It speeds up the reaction. In this case, we have two carbon atoms, a double bond. Ethylene or ethene is the systematic name. Converted to ethane by the addition of hydrogen. You will need to be able to identify and write these types of hydrogenation reactions. I'm going to skip over halogenation. Halogenation occurs according to Markovnikov's rules, and there's hydration, which we will miss too. I want to go back to the fatty acids and talk about whether we want to eat margarine or butter. So as you can see, the fatty acids are made up of very large carbon chains. But at the very end, you will have the COOH group. But there are largely alkenes. It's saturated fatty acid chains. A diet rich in saturated fatty acids is generally considered unhealthy. Alternative versions of butter, such as margarine, they do have some C double bond C atoms in them, which are unsaturated fatty acids. And in general, unsaturated fatty acids tend to be better for you than those molecules containing only saturated, single bonds. In general, again, if you want double bond containing fatty acids or unsaturated fatty acids, those tend to be liquids at room temperature. What you generally end up doing when you synthesize something like margarine is that you take a naturally occurring unsaturated fatty acids and you partially hydrogenated, that is, removes some of the double bonds but keeps some of the other double bonds, so that these are no longer liquids. These are now solids, but then they do have a few C double bond C in them that make them healthier, supposedly. And so this is a structure of some of these oils. You can again see these C double bond Cs here. What we do with these oils is to hydrogenate them. So get rid of some of the C double bond Cs, but not all of them. So you see some of the C double bond Cs still there, but some of the C double bond Cs taken away. And you can see that the oils are liquids, whereas margarine or a butter alternative is neither butter, which is only single bonds, nor is it oil, which has more double bonds. Something like margarine has an intermediate number of double bonds. There's also, although this argument that when you do this in margarine, for example, what you get is trans bonds. So once again, I want to show you what trans would mean. If you had two substituents, the two substituents would be on opposite ends of each other. And trans fatty acids are considered just to be as unhealthy as saturated fatty acids. And so nutritionists, butter as well as margarine, butter only has single bonds, and so it's bad for you. Margarine, yes, it does have some double bonds, but it's still bad for you because the type of fats that you're getting is trans fatty acids and not a cis fatty acids, that like what is naturally occurring in a fully in a oil.